Hey everybody, happy Halloween to you. I got some, in the spirit of Halloween, I got some scary math and some calculus, and today I'm just going to kind of jump into it. But I gave you section 12.3, and if not, I'll be sending it to you as well, and 12.4, so just have that available. And just kind of like in class, as I'm going over it, you can kind of take notes and fill in as necessary. Um, on this first part, a lot of this is on your notes, so you don't necessarily have to write it. Just kind of follow along. Now, let me talk about a few functions that we've done in the past. For instance, this is f of x equals to 1 over x. And if I want to find the limit, just to remind you, and again, this is on your paper, from the positive side. Okay, so what does this mean? As I'm going on my graph, and as x approaches 0 from the positive, or in other words from the right, what are my y coordinates approaching? Infinity. Okay, so that's why that limit's infinity. If I do this same limit from the left of 1 over x, and I'm going from the left, and now I'm approaching 0 from the left. 0's right here. So I'm getting closer and closer and closer to 0. Well, this goes to negative infinity. Then if I do the limit as x approaches 0 from both directions, well, remember what we said a while back. If they don't match, if the left-hand limit doesn't match the right-hand limit, then the limit does not exist. Okay, so that's a limit with f of x equals 1 over x. Let's try maybe one more. So we can do here. Let's do f of x equals 1 over x squared, which to me this one looks like a volcano. So this one we can kind of play around with some of the limits. The limit as x approaches 0 from the left of 1 over x squared. The limit as x approaches 0 from the right of 1 over x squared. And the limit as x approaches 0 of 1 over x squared. And just kind of like in class, it might be good for you to try some of these beforehand. So see if you can think about it. Pause the video, look at it, see if you can think about the answers to these. Take 30 seconds or so. But okay, assuming you did that, from the left, what's it approaching? This is going to infinity. From the right, because it's positive, as I go to 0, my y coordinates are approaching infinity as well. So does the limit exist? Or does the left-hand limit equal the right-hand limit? In this case, yes. So that means the limit equals infinity. Okay? So in that case, that limit exists. Okay, but let's do justice and do maybe a few more. So there's also y equals e to the x on your page, which y equals e to the x looks like any exponential function. And we can get a couple of limits. The limit as x approaches 0 of e to the x, the limit as x approaches infinity, or let's start with negative infinity, e to the x, and then the limit as x approaches infinity of e to the x. So these three limits, as x approaches 0, well, the limit as x approaches 0 is going to be right there, that number. And remember, what's the first thing we try with limits is direct substitution. So if we direct substitute 0 into x, I get e to 0, which just so happens to be 1. So in other words, the limit from the left is 1, the limit from the right is 1, because e to the 0 is 1. So that's the limit of e to the x. Again, that brings up an important point. The first thing you try is direct substitution. Okay. And here, if I look at my graph, as e goes to negative infinity, well, if you recall, there's an asymptote right here for exponentials, and as I go to negative infinity, what does my y coordinates get closer and closer and closer to? Well, it's never going to pass that asymptote, So it gets closer and closer to the number 0. On the other side of it, as x goes to infinity, what do my y-coordinates go to? Well, my y-coordinates will go to infinity. So that'll be the right-hand limit there. And then just last one, this one. I did 2 extra than I thought I wanted to do, but just to kind of give you the full picture. You have natural log of x, which is going to appear this way. And if you notice natural log of x, there's actually a vertical asymptote at x equals 0. But let's look at some questions with this. I could say, what's the left-hand limit, or what's the right-hand limit first, of natural log of x? And what's the limit as the natural log of x approaches infinity? Okay. Yeah, I know I got a little sloppy here. So x approaches infinity. Okay, so from the right-hand side, if x is approaching 0 from the right, what does my y-coordinates approach? Negative infinity. And as x approaches infinity, what do my y-coordinates approach? Now this may not look like it, but it's going to keep going upwards. Okay, so a little more slowly than the exponential, which looks like that. But it's increasing, so that also, the y-coordinates will go to infinity as well. Okay, so that's just like a quick review over limits, which we did on week 1 and week 2. And so I want to talk a little bit more about some of the ones that we did in the past. Like, for instance, there's one on your paper as well, x squared minus 4 over x minus 2. And things like these, if you can factor, it's usually a good idea to factor. So then you'd have limit as x approaches 2 of x minus 2, x plus 2 over x minus 2. And then what do you notice? Well, the x minus 2's can cancel out, leaving you with the limit of x approaching 2 of x plus 2, which now I can direct substitute, which kind of takes me back, because just 2 plus 2, that's 4. So I should have tried in the beginning to direct substitute, but that was the problem there. If I try to direct substitute 2, the top's fine, but the bottom, what do I get? I'll get a 0. So 2 minus 2, that's 0. I can't divide by 0, so there's a problem. So that means I can't direct substitute on this limit. So therefore I had to do other means, factored it out, saw that something canceled, and then we end up with this is x plus 2. So this graph actually looks like x plus 2, y equals x plus 2, where the y-intercept is 2, and my slope is up 1, right 1. So that's what this graph looks like, and then this indicates that there's a hole at 2. So there's a hole at 2, so my graph actually looks like that. Okay? And then you can put this in your graphing calculator to verify that it does look like x plus 2, but that's what it's going to look like with a hole there. And that's how you're able to solve that. Okay, so let's go to, so all this is actually just review. Everything I just talked about from week 1. So what I want to get to is limits like on the back, which is the limit as x approaches 1 of e to the x minus e over x minus 1. Okay. Right now we have no method of solving this. So we have to use what's called L'Hopital's rule, which is right above this on the back. It says, for c, a real number, if the limit of f of x equals 0, the limit as x approaches some c of f of x equals 0, and the limit as x approaches some c of some other function g of x equals 0, then the limit of f of x as x approaches some c over g of x, which you can kind of see there's a fraction here, f of x over g of x, that's f of x, that's g of x, equals to the limit of the derivative of f prime of x over g prime of x. Okay, so we're actually going to apply some of the derivative ideas here. So first things first, check that these are true. Does the limit of e to the x minus e as x approaches 1 apply there? Yes, because, and this is the check, limit as x approaches 1 of e to the x minus e, direct substitution says e to the 1 minus e, which is e minus e is 0. So the first check, it goes through, okay? Second check the bottom. Does the limit as x approaches 1 of the bottom g of x, using direct substitution I get 1 minus 1, that's 0. So does that check out? Does the limit as x approaches 1 of the bottom equals 0? Yes, that checks. So then I can apply L'Hopital's rule. Okay, so L'Hopital's rule would be to the limit, I'm just going to copy the question here, as x approaches 1 of e to the x minus e over x minus 1. L'Hopital's rule says now that I'm going to take the derivative of the top. What's the derivative of e to the x minus e? Well, and then still write the limit. E to the x is e to the x. E is a constant, so it just kind of goes away. And then what's the derivative of x? Well, the derivative of x is 1. And then now, if you can apply direct substitution, which here is just e to the 1 over 1, which is e divided by 1, which is just e. So that's the limit of e to the x minus e. Okay, so that's how you apply L'Hopital's rule. So I'm going to leave this here. We're going to do some other examples with L'Hopital's rule. But the main idea is, if you can take the limit of the top and it gives you 0, the limit of the bottom and it gives you 0, we call this a 0 over 0 indeterminate form. And if you have something in indeterminate form, that means you can take its derivative in that way. And not only that, it also works for limits that go to infinity, so which we'll see in a little bit. If you have an infinity over infinity form, that's also considered indeterminate form. Okay. All right, so that's that example. Let's take it to another example. So let's try evaluate the limit as x approaches 1 of ln x over x. Okay, and this would be one of those times in class I'd say, okay, go ahead and try it. Take the limit of the top, see if it gives you 0. Take the limit of the bottom, see if it gives you 0, and then work it out from there. But, well, here actually, I think I might have made a question that's just to throw it out there. This one you could actually evaluate right away in direct substitution. So, which is what I said you should start with in the beginning. So this is actually not a very difficult example. So you'll get natural log of 1 over 1, which there's nothing wrong with that. I can evaluate it's continuous. So, but you should know that the natural log or the log of 1 of any number is always going to be 0. You can try it on your calculator. Okay, so that'll give you 0. So let's move on to the next one that I wanted to do, which is a real application of L'Hopital's rule. The limit as x approaches 1 from the positive ln x over x minus 1 squared. Now you will notice something, that this one has from the right side, and these rules don't have from the right side. But if you look at the rule right above this question, it now says it doesn't matter if there's a from the right, from the left, to infinity or to negative infinity. Either it's you can apply the rule. Okay, so that means we can do L'Hopital's rule. So first things first, we check if we can actually use the rule. So we're going to check these first two conditions. So I'm going to check the limit to the top. Limit as x approaches 1 from the right of ln 1. Well, what did we say that was? That's 0. Now I'm going to check the limit of g of x, the bottom. The limit as x approaches 1 of x minus 1 squared. I'll get a better marker. X minus 1 squared direct substitution of 1, you get 1 minus 1, that's 0. Okay, so this is an indeterminate form. Okay, I have a 0 over 0 indeterminate form. Okay, so that means I could apply L'Hopital's rule, which tells me I can take, to find this limit, I can take the derivative of the top of f of x and then the derivative of the bottom and then take that limit. Okay, so let's try it out. So I'm just going to rewrite the limit. Limit as x approaches 1 from the right of ln x over x minus 1 squared. So what's the derivative of ln x? Well, we know that's 1 over x. And what's the derivative of x minus 1 squared? Well, x minus 1 squared, that's going to be, I can use the chain rule here, 2 times x minus 1 times the derivative of the inside, which is 1. So I'm just going to write that. And then I can try, well, one thing I should kind of keep my, I'm going to rewrite the same thing, but just with the limit. So what do we say? Derivative of ln x is 1 over x. Derivative of x minus 1 is 2x minus 1. Okay. And now we can try direct substitution, which on the top, it's okay, but guess what, on the bottom, it's still not okay. Because I'm going to plug in a 1, so what do I have to do? I have a form where I can't get any further than that. So what we're going to do next is we're going to take the second derivative of this. Okay, give me a second here. Okay, sorry for the delay. So I need to rewrite this as limit as x approaches 1 from the positive direction. And this 1 over x I can rewrite as 1 staying on the top and then x on the bottom, but I'm going to put it after the 2x minus 1. And then I'm going to distribute this Okay, and it's going to be 2x squared minus 2x. And this will somewhat be like that volcano function, and you can graph it and then see what I'm talking about. But this actually ends up having what we can see right here, a vertical asymptote at 1. So if it ends up looking like that volcano function, well then as we go to 1, the graph's going to go to infinity. And here's something of what I'm talking about. Here's 1. There's vertical asymptote. It should look something like that. So from the positive side, we know this limit's infinity. Okay, and feel free to use graphs to help you find some of these limits as you get to that point. But the key was to first use L'Hopital's rule. We found a 0 over 0 indeterminate form. We took the derivative of the top, which was 1 over x. Took the derivative of the bottom, which is 2 times x minus 1. Change this around a little bit where we put the x in the bottom. So it's 2x times x minus 1. We distributed it, and then I recognize that this is like 2x squared, which will kind of give me that if there's an asymptote like a volcano shape to it, meaning that the limit as x approaches 1 from the positive is going to be positive infinity. Okay, so that's another instance of the L'Hopital rule. Let me kind of get into let me get into some more detail on this. So let's try the last one, which is ln x limit as x approaches infinity of natural log of x over x squared. So again, we don't know how to evaluate this. I can't do the limit of infinity. Well, and that's the check actually. We're going to do the limit of infinity for the top. Okay, that's going to be our check here. Limit as x approaches infinity of natural log of x. Well, natural log of a very large number, that'll approach infinity. And then we're going to check the bottom. Limit as x approaches infinity of x squared. We'll plug in a very large number. You're going to return another large number. So that's infinity. So it checks out that the first two conditions lead me to an infinity over infinity indeterminate form. Okay. So because I have an indeterminate form, that means I can apply L'Hopital's rule, where I'm going to take the derivative of the top. So I'm just going to rewrite the function here. Ln x over x squared. Take the derivative of ln x again, which we know is 1 over x, and the derivative of 2x, which I know is 2x. And then from, and squeeze the limit in there, of course, x approaches infinity. From the last problem, we saw that I can move the x here to the bottom, so let me do it on the next line. The limit as x approaches infinity of 1 over x times x be 2x squared. This we do know because if x goes to a very large number, the denominator goes to a very large number, and 1 divided by a very, very, very large number close to infinity is essentially what? Well, 1 compared to infinity, that's essentially 0. So that would be the limit. You could also look at it in a graphical approach. If you graph this, you'll see that as you go towards infinity, you'll get this kind of graph. As you go towards infinity, your y coordinates gets closer and closer to 0. Okay, but that's using L'Hopital's rule, and that's it for that section.